Hello everyone, today I'll be sharing with you lessons that I've learned from implementing a key value store using Raft. My name is Omar and I'm a software engineer at Square. This is my second time at the P99 CONF and I'm really excited to be here and I hope you all are excited too. When I started using NoSQL databases, I thought about how these databases work behind the scene. I then came across Raft, a consensus algorithm to build a fault-tolerant, highly available systems that store and replicate data across different servers despite failures. And my hope was to go through the journey of implementing a key value store and the micro lessons one can learn from it. So our today's goal is to build a key value store that achieves the following. First, fault tolerance. Second, consistency guarantees. This means the system behaves in a way as if all operations are executed on a single machine despite having many nodes. Next, performance guarantees. System should be equivalent to other consensus algorithms. And last, system should be able to recover from failures. In our first attempt, we have the ROWA approach, which stands for read one, write all. And in this approach, we have a few servers, one leader, and rest are replica, in addition to a configuration server that acts as the brain. It detects failures, elects a new leader, and spins a new node. For reads, the leader reads their in-memory data and replies back to the client. For writes, however, leader has to wait for all replicas to replicate the data before it replies back to the client. This restriction achieves a strong consistency guarantees as it prohibits reading stale data. For handling failures, the configuration server detects node health by exchanging heartbeats. When the configuration server detects a faulty replica, it tells the leader to ignore it to unblock by processing. And if the leader failed, the configuration server will elect a new leader from the remaining replicas. So writes will be temporarily down if any node is down, while reads will continue uninterrupted unless the leader is down. Raft is a majority-based consensus algorithm, and perhaps the biggest difference here is that we only require a majority of servers to replicate before responding to the client. There is no configuration server, no single point of failure, and nodes talk with each other to replicate data, detect failures, and elect a new leader. So the leader broadcasts a client request to all followers and waits for a majority of servers to respond. Now, reads can be done at the leader without broadcasting, but certain conditions have to be met, and we will dive into this later on. For handling failures, leader and followers exchange heartbeats, and leader can still function with slow or faulty follower as long as the majority of servers are still up, and the slow follower will eventually catch up from where it left. Followers will elect a new leader if they haven't heard back from the current leader for an election timeout duration. So here's a quick comparison between these two approaches. Raft is more complex with different trade-offs. Raft does not rely on a single master to make critical decisions, and for a long time the read one write all approach dominated the data replication, but majority approach have been gaining ground due to their toleration of temporarily slow faulty replicates. Okay, so let's talk about the building blocks of Raft. First, the log replication. This is the backbone of Raft. It's a write-ahead log. It's a simple data structure to replicate data and ensure consistency among all servers. It contains all commands sent by the client and applied on the key value store. The key value store live in the main memory, but the logs are also persisted to the disk for durability and replicated to all followers for redundancy. And the leader is responsible for replicating the logs among all followers. But the question is, why should we keep the logs when we already keep the key value stored data? Well, for many reasons. It is to order the log entries so that we have a single execution order. It helps the leader ensure followers have identical logs and to resend the missing logs to lagging followers. It helps with electing a new leader with the most up-to-date logs. And finally, it allows log replay after server crashes and reboots. And we will talk about elections and server recovery later on. Applying or executing a command in the log entry is a two-step process. First, a leader broadcasts a log entry to all followers for replication. And when the log entry is replicated by a majority of servers, including the leader itself, leader executes that log entry command and tells all followers to execute it as well. Now, some followers may lag, and we will see they can temporarily diverge, but the good news is they will eventually converge to be identical, and the leader will resend the log entries when the followers is up again. There are some properties that the log replication guarantees. First, if any server applied a given command in a log entry, then no other server executes a different command for that log entry. Second, we cannot roll back applied log entries. For example, if a client received a successful reply to a write request, then the log entry persists despite failures as long as a majority of servers are eventually able to recover. And finally, log entries can be overwritten. For example, if a leader tried to replicate a log entry, but it failed midway and a reply was never sent back to the client, when a new leader is elected, it may choose to override this log entry if it has not been replicated on a majority of servers. The next topic is network partitioning. What happens when servers cannot talk to each other? If a follower is partitioned, it will catch up when it rejoins, and the leader will resend missing logs. If the leader is partitioned, however, a new election will start, and this will result in another leader accepting and replicating client requests. And the previous leader may continue to accept client requests and will try to replicate to followers, but because the previous leader cannot talk to a majority of servers, the logs will not be applied and will be ignored. Eventually, it will learn about the new leader from other cluster nodes and step down to a follower. What we just described is what we call the split brain syndrome. This is when two leaders are up and running at the same time, and this can violate the consistency guarantees as one leader might reply with a value that has been recently updated by another leader. The good news is the majority rule guarantees that a leader has to get a majority of followers' agreement before replying back to the client. We previously talked about the leader and followers exchanging heartbeats. When a follower does not hear back from the leader, it starts an election. So here's how it works. First, a follower becomes a candidate and starts an election by collecting votes from other followers. Other followers only vote for the candidate whose log is at least as up to date. And when a candidate gets a majority of votes, including a vote for itself, it wins the election and becomes a leader. So at most, only one leader can win majority votes and the election. The new leader sends heartbeats when elected and periodically to all followers to maintain its authority, and the previous leader will eventually step down as a follower. One of the common techniques to hold a lock in distributed systems is to use heartbeats. They are a form of a time-bound lease, a contract to be renewed periodically. This is useful to prevent concurrent actions, for example, accessing a shared data or processing a job concurrently. And because it's time-bound, the log is not held indefinitely in case the leaseholder was disconnected. Now, a common question is, what happens if two candidates started an election around the same time? Votes granted by followers might split between these two candidates evenly, and neither one can win the election. So they will keep on retrying, but this can go on multiple times. One solution is to use randomized election timeout. Followers that have not heard back from the leader, starts election at different times. Chances are a candidate completes the election and becomes a leader before everyone else. Randomization is one of the interesting and simple techniques to reduce contention. I previously talked about randomization in a bit more detail at the P99 CONF last year. Moving on to a new topic, how do we recover the in-memory key value store after failures? So when a crashed server reboots, it rejoins the cluster and catches up from where it left. An easy approach is to start with an empty state and replay the whole Raft persisted log. But the log might be huge and can grow without bounds and will take a long time to replay. An alternative approach is to use snapshots. So each server takes a snapshot of the in-memory key value store periodically, and now it's safe to throw away all the logs appended before this snapshot was taken. On a server crash and restart, it first loads the snapshot and the persisted log from the disk and applies all log entries appended after the snapshot was taken to create the current key value store state. There are two common performance issues with taking snapshots. First, we need to determine when to take a snapshot. Is it based on a log size, a fixed timer, or something else? Ideally, snapshot schedule should balance between resources and performance. Second, how to unblock processing of write requests while taking snapshots. There are a few techniques, and one of them is the copy and write technique. An implementation of this could be found in the Linux operating system fork method, which creates a child process that share the same memory pages, and only when the parent process updates the memory, a copy of the memory page being updated will be created, and therefore not affecting the child process. So Raft snapshot logic, at least in the naive implementation, is reasonable if the key value store is small. It simplifies the logic by always copying the entire in-memory key value store. But if we have a lagging or slow follower and the leader deleted part of its log while taking a snapshot, the leader might need to send a copy of a snapshot in chunks over the network. And for storing large amounts of data, taking snapshots and dealing with lagging followers by replicating gigabytes of data is not scalable. So one thought here is to use incremental snapshots by remembering which parts of the key value store state have been updated. An example on this could be the LSM trees has an in-memory table where all changes are added and periodically flushed to the disk as a sorted array of key value pairs. So up until now, we have been sending read and write requests through one leader. This was to ensure strong consistency and it also simplifies the logic. But it's clear that the leader is doing all the work and therefore becomes the bottleneck. So can we do better? The answer is yes, we can. I will start with scaling reads and then discuss scaling writes. But before we dive in, let's remind ourselves with one of the consistency guarantees we have to fulfill, and that's the no stale reads. The key value store must reflect the behavior of a single server. For example, read request started after a write request has completed should see the result from this write request. So to scale reads, there are two questions one might ask. First, can followers respond to read requests? So followers cannot unless we avoid stale reads. And for this to work, one quick thought here is for the follower before it replies back to the client, it makes sure that its local value is consistent with a majority of servers. There's a paper here from CockroachDB discusses the implementation of a majority reads from followers. The next question is, can leaders respond to read requests without broadcasting and applying log entries? The answer is yes, under two conditions. First, no split brain. When two leaders at the same time, when you have two leaders at the same time, one leader might return a stale value that has been updated by another recent leader. So one possible solution is to use leases. So after each time the leader exchange heartbeats with a majority of servers, it is allowed to respond to read-only requests for a least timeout duration without broadcasting to followers. And if a new leader is elected, it will not execute write request until the lease timeout expires. Second, the no-op operation. A potential problem is when a leader fails right after it replicates a log entry on a majority of servers and replies to the client. Later on, when a new leader is elected, it has to make sure all previous logs have been applied to its own key value store so that future client requests will get the same value returned by the previous leader. And for this, the new leader must append and apply a no-op operation in its own log at the start of its term when it gets elected. Now, let's talk about scaling rights. And as usual, before we dive in, let's remind ourselves with one of the consistency guarantees. And this time it's the ordering and the concurrent rights. The state of the system at any point in time must be the result of sequential execution of some operation in the same order they were sent or received by the key value store. And the concurrent operation can be executed in any order as long as all clients see the same sequence. Our first optimization technique is batching, and it is to batch multiple client requests in order to send them over the network and to write them to disk. Batching optimizes throughput, especially when the system is under heavy load, so it's only effective if the leader sees many client requests at the same time. Next, we have pipelining. So the naive way of sending batches is to replicate one batch at a time. So pipelining here is to send the next batch to followers without having to wait for the previous batch to finish and therefore optimize latency. So the leader can send the next batch, for example, halfway through the first one, therefore reducing the average latency by half. And finally, we have parallelizing. So this one is to separate and parallelize independent operations. For example, leader can write log entries to its disk in parallel with replicating logs to followers. To put everything together, client send write request, leader batches them, and when the batch exceeds the size or the time threshold, leader will persist it on the disk and replicate it to all followers in parallel. In the meantime, leader is preparing the next batch and will replicate it soon without having to wait for the previous one to finish. Here are some useful resources to learn more about Raft. Thank you.